It's obviously a problem. I mean, my laptop recognizes it, but the screen doesn't. Oh.
Okay.
Now maybe? Okay. Okay, can we start?
The stream is on.
Okay. There's still something we need to do from yesterday's lecture, but I will do that after this one for two reasons. First of all, it will be easier to understand after this one. And secondly, because this one maybe needs more concentration, so while you're still awake. And so today is about two very important type classes in Haskell called monad and applicative. And they are have quite a reputation in Haskell that they are a difficult concept. But once you have understood those, then basically the rest is smooth sailing. So in that sense, today's lecture is maybe the most important one. Right, and I will diverge a bit from the slides, especially in the beginning, to try to motivate it as far as possible. And first, for the first hour or so, we won't mention this and just look at things we have already done. But there's a reason for that, of course. Let me make it bigger. Right, so I started an empty module, and maybe first thing, there was this table type. I probably should, was that in the first lecture? Yeah.
It's in the second, I think.
Let's just see.
03.
I had this second. And then I did another thing where I put it in its own module.
Yes.
Do you remember when that was?
I think that's the 03, because in 02 we presented.
Oh, but I only, must be 05 then, because of 1, 2, 3, 4, I don't have anything here.
At the very bottom, 03 data.
Oh, right. Let's see.
See if there's there.
Nope.
There isn't. Oh, yeah. There's
Nope. But I'm pretty sure I had it somewhere.
Polymorphism, that classes, 04.
Oh, that one, yeah.
It was its own file, right?
I think it was in its own file. But anyway, then I introduced it here in 3, right?
Yeah, maybe.
I mean, I can copy. Oh, that was the last example. Here, this was the.
There. Inside, yeah.
Right, so I can just copy this. Let me just copy that into today's. And I call it table. And let me switch back to here. And now I must modify the cabal file, because now I want to use this table thing. So in the cabal file, now I have 2 modules. I think I don't need a comma there. Let's see. Let me open that and rename it to table. Delete stuff. Empty insert delete. languages. And I get the error because it's also in the prelude. So I must import prelude hiding lookup. Okay, and now I mustn't export everything. So just the type, not the constructor. And what was it? Empty. Insert.
Delete. Lookup.
Okay. See whether that builds. Yeah, looking good. So I reload the window just to be sure. Okay, so now we should have this table available. And I should import it qualified because of this clash with lookup with the prelude. Qualified table as T, for example. Okay. And we did have this example with the transactions, so I want to basically revisit that and maybe do it a bit differently. So let me define this transaction type, and so that I don't have to write so much. I just call it TX. And I don't know what it was called back then, but I just... okay, first of all, let's say accounts is a table from, let's just say, string. I think we had some different thing last time. So that's the owner of the account, and I don't know, int. Although it shouldn't be negative, so maybe just for variety, let's use natural. So that's the type of natural number, so it can't be negative. And it's arbitrary precision natural numbers. Import, that's numeric, natural. So, I mean, we could use int, but I just don't want negative accounts. Although, yeah. Right, okay, fine. Table, yeah, normally, I mean, I could write t.table because it's qualified, but in situations like that, often one imports it again and then just the type, just the type. So basically the operations are qualified, but the type itself is not, so then I can just write table. Okay. So this is just, I mean, you can imagine I could also call it bank or whatever, bank. So that's the list of all the accounts and their balances at the bank. And a transaction, I don't know what we called it last time, it doesn't matter, it doesn't have to be the same type, so let's call it tx from is a string, tx2 is a string, and tx amount is maybe also natural then. And I can deriving show. I mean, I could derive more, but it must be a small t. Right. And now I want to do transactions, so perform them. But there can, I mean, lots of things can go wrong. I mean, and we handled that differently last time, but it doesn't matter. I mean, it's just an example. So, I mean, at least 3 things can go wrong. I mean, from couldn't exist, to couldn't exist, or the amount, or the from doesn't have the necessary amount to do that. So at least those 3 things. I mean, we could argue whether transferring 0, for example, is okay. And we could also argue whether from is allowed to equal 2. So maybe we should forbid that as well. Right. Okay, and now I wanted basically a function process transaction. But so it gets a transaction and it gets a bank, and it is supposed to update the bank. But because that can go wrong, let's do a maybe bank. So if there's something wrong with the transaction, I return nothing, and otherwise just the bank, the new bank. Okay. TX. And first I can check these things that I just mentioned. So if the tx from equals tx2, or if tx amount equals 0, then I immediately stop and say nothing. Okay? And otherwise, okay, first, I need the balances of from and to. And we had this lookup function, and that can fail if the key doesn't exist. Okay, so case t.lookup takes a key, so that's in our case tx from tx, bank of. And now there are two possibilities: it doesn't exist or it does exist. So if it does not exist, so it's nothing, then I fail. So the overall result is nothing. Or it could be just, I think last time we called it old from. Okay. So now I must do the same for 2. Or actually now I could check whether that's sufficient. So if old from is less than tx amount tx, then nothing, I can't proceed, and otherwise I can go on. Right, now I must check whether 2 exists. I think we didn't last time, but in a real bank you can't transfer money to an account that doesn't exist. So T, and probably I can put it here. T lookup tx from tx, sorry, 2, of course. Bank of. So again, now maybe that does not exist, in which case, again, I'm done. Or it could exist with the balance old 2. So now I can proceed, so I can say, okay, new from is old from minus tx amount tx. New 2 is old 2 plus tx amount tx. And new bank, or now I can just return the new bank, so just. And now I must update the balances. So I have t insert tx from tx, new from, t insert tx2 tx, new 2 in bank. And what's wrong now? Oh yeah, sorry. Okay, so that's that, and that's nothing new. That's all like last week or even beginning of last week. And there's something wrong. Oh yeah, I forgot the tx here. I wonder whether I should introduce record puns.
Maybe.
Actually, this is a common thing. We see that are always, these accessor functions are just functions that I have to apply to the value, of course. And that is sometimes a bit irritating because I have all this duplication here. I always have to apply to tx. There is an extension. This is not topic of today's lecture, but it's useful to know. I think it's called record puns, or is it wildcards?
Wildcards.
Record wildcards. Record wildcards. And then I can do something like this. I don't even need to give it a name. Sorry. Sorry. So then instead of this here, I can say tx and curly brackets with 2 dots. And now I can leave this everywhere. So this is just an extension to make it easier, to work with records, because that's a common case. You have this one record. Of course, if we had 2 different transactions, this wouldn't work. Again, this is not the topic of today's lecture. That's just, it's frequently used, so I should show you. Right. Okay, and I don't know, maybe we should have an example bank and example transactions or something. So bank, okay, let's say, I don't know, Robertino starts with 100, and T insert Marina 250. Right, and now we could first do a, okay, let's say, I don't know, doesn't matter, tx1, tx2, so that, okay, and doesn't matter, I'm just, whatever. And now if I should be able to try this. If I first start the REPL, what was the problem there? It looks fishy.
Yeah, no, not start.
Right.
Yes. Initial.
Yeah, okay. Initial bank. Okay, fine. And now I can try. So, for example, if I do process transaction tx1 initial bank, I get nothing because Robertino doesn't have enough funds to send 150 to Carina. And if I do tx2, then it works. So hopefully, so Carina afterwards has 180 and Robertino has 170. And now I could, for example, do let bank 1 or whatever, or just bank 1 equal this. It doesn't matter. So this is just annoying. So this is now the new state. And now I could do process transaction tx1 on this new bank after the Carina is transferred. And now it works. And Robertino is left with 20 and Carina with 230. Anyway, but so that works, but it's not about transactions today, it's about like programming style. So if we look at this code, it's annoying. It goes further and further to the right, and there's a lot of repetition. Because I frequently, like at least twice, I have some, I do these lookups, and they result in a maybe. And then I always do the same. If what I look up is nothing, I return immediately, stop the computation with nothing. And if it's not, then the rest of the computation depends on the just value. And this is twice here. And it's relatively frequent, so often, I could come up with examples where it's 3 or 4 times. And then it would dangle more and more and more to the right. So that's an anti-pattern. If ever in your code you have something like that, then there's something fishy. It's correct Haskell, and it works. But I mean, first of all, it has this thing, and secondly, Haskellers don't like code replication. So we try to abstract that away. So again, we have some maybe value. We do a case over it, and then if the maybe value is nothing, we stop with nothing. And if it's just something, we proceed with the computation that can depend or does depend of this value. And that happens twice here. So let's try to abstract that away. I call it for mysterious reasons maybe. So we have some maybe value. And in the case that is a just, we have some way to proceed. And then we proceed. So let's call it M and F. So I basically just copy what I did there. So I do a case, and if the M is nothing, I immediately stop with nothing. And if it's just something, I apply the given function f to that x. And why is this? Oh, case off, sorry. Yeah, this, yeah, I don't even want to. Although that probably says that it's maybe, I could apply maybe. Yes. So we can, I mean, this equivalently, if I follow the hint, I could write that as maybe nothing fm. I mean, so actually I could write this. So this is morally what we want to do. And this is exactly, I mean, the pattern I used. But the nicer way following the hint would be maybe nothing fm, and yeah. And yeah, okay, that I ignore. But okay, whatever. I mean, it doesn't matter. And now I can use this, so I can now simplify my code. So I wonder whether I should, maybe I copy it, and yes, because it's better that you still have this old one. So I basically just write the same function, but using this bind maybe. Let's call it process tx prime. Right, and I mean, there are two occasions where I can use this. So
maybe can you leave the older definition, the more verbose definition, because it matches better instead of the maybe catamorphism?
Yeah, sure. I mean, that's why I left it as a comment, but it doesn't matter. Right. So what now, in order to apply this new cool function, I must identify the M and the F. So the M is the maybe I'm pattern matching on. In our case, that's this. So I can now just keep this. And for reasons that will become clearer later, I mean, it's better if I use this infix now. And now I need this f, which can depend on the just value. So I called that old from. Okay, and now I can delete this. Now it's a bit, maybe it wasn't such a good idea. So I must do something with this guard, so I can, for example, do an if, right? If, so I replace that with nothing, and nothing else. Okay, now it continues. And now I have the second occasion of this, so I can use my bind maybe again. And now it's old 2. Right.
There's an error function application, line 56.
Oh yeah, I didn't want the. Oh, no, actually I wanted to.
You have to
Oh yeah, sorry. Yeah, sorry about that. Okay. So this is just, I mean, how did I get there? I mean, first of all, it's simpler. I mean, it's shorter. How much shorter? I mean, it's now from 52 to 65, so that's 14 lines. And it used to be from 17 to 34, which is 18 lines, I think. So I saved 8 lines of code. And it's not dangling so much anymore, but it's still dangling a bit. Because of this if thing, and I mean here as well. And that's also actually a pattern that we should probably identify and get rid of. But again, I mean, the process is the thinking process. I identify this common pattern here. I do a pattern match, a case statement on a maybe, and then if it's nothing, I stop with nothing, and if it's just some variable name, I proceed and may use the variable name later in the computation. And this happened twice. I mean, it was here that I did this, and it was again here. So what I've done is abstract that away in this thing I call bind maybe, and applied this. So now it's shorter and nicer, but not wonderful. So, I mean, let me just improvise here. So, I mean, this is now not like planned or anything, but I mean, it's still annoying because here we have, I mean, twice we do the same thing. We check some condition, and if that's true, we return nothing. And if it's false, we proceed. We do this here, and we do it here. I mean, normally, if I now just abstracted that and didn't know what I know, I would basically do what I just said. So if the condition is true, nothing. However, that has a name, and so I do it the other way around. So if the condition is false, I do nothing. And I call it guard. Guard maybe. Guard maybe. So it takes a Boolean, and I'm not sure. I mean, I could just say maybe unit, but that is maybe a bit too adventurous. I mean, it doesn't matter. Maybe I should just not bother and do what it looks like. I mean,
more confusing.
It's more confusing. Let's just, whatever, check maybe or something. So it gets a Boolean and maybe A, and then maybe A. So the idea is, so this is now just my invention here. So that's not, but anyway, it would be the normal process if one did this and tried to identify patterns. So condition, a B and an M, and if the condition is true, then I immediately stop with nothing, and otherwise I do my M thing. Okay, and if I use this, then I can simplify this here and this here. So it would be check maybe, so what's the condition here? Tx from equals to so this. Okay, and then I can do it again here. Check maybe like this. Okay, so now it's, the only annoying thing is, I mean, I still have like an indentation. So normally, maybe in the end, we can see how to get rid of that. Right. But I mean, it's definitely nicer. Now it's even shorter. Now it's how much lines? 57, 68, so 12 lines. So I saved again to my lines. Now at least it fits on the screen, even with this insanely large font. Okay. So again, so we identified like a common pattern, sum of for maybe, and then applied that. And we saw another pattern and applied that as well. But that's non-standard, this check maybe thing. I just made that up. And it's not ideal, but we can talk about that later. And looking at this bind again, so the idea is you have some computation that may fail, like in this case looking up a bank account that may fail if that bank account doesn't exist, and some way to, if it didn't fail, to go on. And then there's this common pattern that if it fails, we immediately stop with nothing, and if it doesn't fail, we go on with the given, I mean the fancy term is continuation, but that just means way to proceed. And if you think about it, it's a bit like throwing an exception in an imperative language. So this case here is basically the exceptional case, and the computation immediately stops with nothing. And this is the normal case, the good case. So one can think of this as a way of introducing exceptions into Haskell in pure code. I mean, there's no I/O involved. It's just everything is pure. And of course, if you think of exceptions, then maybe it would be nicer. I mean, here, I mean, I should, maybe first of all, I should check whether we still get the same results. So, I mean, I had this one, if I now, which failed. So if I now do the primed version, still fails, and the non-primed one still succeeds. So I mean, I didn't change the meaning of anything, just made it nicer. Okay, and now of course, in the first case, it's a bit annoying that it just fails, but we don't know why. So might be a good idea to change that. And I mean, the problem is that maybe it doesn't have a way to signal reason for failure. I mean, there's only nothing. We know there is no result, but we don't know why. But we do have the either type. And one common use for the either type is exactly that, like a maybe on steroids, where it can carry error information. So for example, so let me do a third version of this. Maybe I start with the original one again.
Mm-hmm. Maybe show the data type.
What data type?
Either data type definition.
Yeah, I mean we have had it before, but I can repeat that, of course. Let me just paste it here again. So yeah, just as a reminder. So so either was this type that has two type parameters, A and B, and then a value can either be a left or right, and the constructors are left or right. And this is completely symmetrical, so there's no, but I mean, so often it's used for whatever harmless things, but if it's used in this context of errors or exceptions, then basically you use the A type for error messages, so the left case is the exceptional case, and the right case is like the good case. And the mnemonic for that is, I mean, right. Right is good. So it's right. But of course, that's only a convention. I mean, more or less a convention. Not really, but anyway. One could do it the other way around. But that's a convention. If you use the either type to like signal error, then you'll use the left for error. Was there a question? No. Okay, so now let me beef this up a bit with, instead of maybe using either. So I don't return a maybe bank, I return either string bank. So the error message. Okay, and now let's see. So now of course I will get, oh sorry, it was the wrong one. This one. So either string bank, and now I don't know, E for either. So of course nothing is now not a nice word anymore. I mean, it's still a nice word, but it's typed wrong because it's of type maybe, and I need an either now. And I just said in this case I want an error message. So left, and now I can come up with something. So maybe actually now, because I mean I mangled those two cases together because for maybe it didn't matter, but now if I want an error message, maybe I should have three cases. So in this case, I can say whatever, sender equals receiver or whatever. And in this case, I can say zero amount. Yeah, exactly. I just want to, because just to make this clearer, I just want to define a function throw error from string to either string A it's just left, just a synonym for left, just to specialize to string, and I just want to make this clearer, that this is like thrown an exception. It's still the same thing. So now here I can say throw error insufficient funds, for example. Unknown sender.
I think they are switched. The first one is unknown sender, the second one is insufficient funds.
That's right. What?
The insufficient funds and unknown sender are switched.
Oh yeah, sorry. Yes. This is unknown sender. And this is unknown receiver. And this is, yes, of course, insufficient funds. And of course, I could make it even more informative. I could, for example, say how much funds are missing if I wanted to. I don't know, do I want to? Maybe I want to. Just to show that, it doesn't have to be static strings. It can be...
Maybe once,
yeah. Just to show you that it doesn't have to be like hard-coded strings. Show tx amount minus from. Okay. That was that, and okay, and now this here is wrong, just because that's for maybe, so now we must replace that by right. Okay, first we can try it out. So this was now process txe, and now, okay, it's good, but right. So now it doesn't only fail, we do get a nice error message why it fails and even how much is missing. And if we do the second one, then we get a right result with the as before. And now, of course, we have the same critique as before with this dangling stuff. So we should, what we did before, we had this bind maybe. Let me now just do the, so let's try to do the same for either. Sorry. So now we have an either, and I'm not sure whether I should use string or e. Doesn't matter really. So it can be. It doesn't have to be strings. It could be some other type of exceptions. And we have a way to go on. Now I should probably call it, I don't know, x. So now, of course, it's not nothing and just. It could be left an error message, in which case I just immediately stop with that error message. Or it could be write a result, in which I continue with that result. And name shadowing, right. Let's call it A because it's of type A. Okay. And now, of course, I can again apply this. So I used it in two cases, here and here. So I can now replace that with my new bind either. So, the code is, sorry. Oh, the indentation was bad anyway. Sorry, let me just. But your stylish Haskell doesn't fix this, does it? Oh,
Should.
okay.
It should.
Maybe. I'm just fanatical about indentation. Right. Okay, so now I use this bind either instead of bind maybe. Hang on, no, something is wrong now.
I think maybe you copied the wrong one.
Yeah, hang on.
No. No, you didn't change the nothing and just
That's right.
to write and yeah.
I did copy the wrong one. I did copy the wrong one, so let me just. But now I'm confused.
No, I
There's
think
this.
you forgot to change the nothing previously. Like
Yeah, but I did try it out already. The process at some point the process txe
yes.
was right.
Yes, you're right.
Sorry, let me just delete this again. I somehow.
But there's just
So I must copy this
no,
one.
because of the lookup. The lookup returns just
Yeah. This is also exactly. So I must do something else now.
yeah.
Right. Right, and right, and I can't apply this bind either now because I mean the lookup is still the lookup which returns a maybe. So what I should do is replace the lookup with a version that returns an either. And I mean the error message is now a bit tricky. I mean, it's fine. Then it's fine. Yeah. So let's do a beefed up version of lookup that works in either. So I mean, what was the old version? It got a key, so a string, and a bank, and then it returned a maybe. It returned a maybe natural. But now let's do an either string natural. And right.
You might need a message.
Yeah, so account, yes, and I need like a custom error message. So let's give it another string in case it doesn't exist. So let's call that message.
Maybe hard code sender fix doesn't exist.
Yeah, but it's also receiver. I use it twice for different ones.
Yes,
That's the
yes,
problem.
right.
Anyway, so there I can. Why is this stupid editor? So so the old lookup, account, bank of. So if it's nothing, if it doesn't exist, then I throw error message. And if it does exist with an amount, then I succeed with amount. Okay, and now I can here use my bind either when I replace this old lookup with the new lookup, and I must just give the error message. So in this case it was unknown sender. And now I can use my bind either, and the new value is it's called old from. So now I can get rid of this. And now again, same thing. So replace this old lookup which worked in maybe with the new lookup which works in either. with the error message unknown receiver. And now my bind either. And maybe I should somehow, because the font is so big, like this. And that was old 2. And can get rid of this. And can okay.
Function application at the top.
Yes, yes.
And the other one.
So tried so hard to think of that this time. Okay, and let's see whether it still compiles. Yeah, and now I should again if I now use the primed version, I still get the right error message, and if I use the second transaction, I still get the right result. So, I mean, I could now do the same thing again with the check. Maybe I shouldn't, and then do it properly.
Right.
And then I can also do it properly for either. So yeah, one could do the same thing again, this check thing now, to get rid of these two cases here. But I leave that now. So again, the idea is there is this common pattern. I mean, so again, maybe. So the idea for this bind maybe is you have some computation that can fail, and if it doesn't fail and you have a result, then you know what you want to do next. And you can do this by pattern matching on this maybe. If it's nothing, you stop with nothing. If it's just A, then you know how to proceed, and you proceed. So that's this pattern, and we saw that it's a common pattern. So we have something that can fail, and something else that can fail, and so you do the first thing, and if it fails, you stop. If it doesn't fail, you have a result, and you proceed with that result. And the same thing we did again here with this either. The only difference is that now, instead of just stopping, we also give a reason why we stop. So it's, like logically, or in principle, more or less the same. It just gives more information in the exceptional case. And so we can throw errors of type E. So but it's basically the same. We do the first thing. If it succeeds, we proceed. But if it fails with an error message, then we stop the whole thing with an error message and don't go on. Okay, so that's 2 examples of this, but it has nothing, it's all stuff you already in principle know. It's no new concept or anything, it's just an example. Are there any questions at this point? Okay. Then we can go to a new example. I'm not sure whether I should start with the tree labeling, maybe tree labeling first, and then. I'm sorry?
Then make everything at once. So all the examples first?
Yeah, all the examples first. Okay, so forget about transactions and banks. Now completely different example, trees. So we have our data tree A, which, what was it? It can either be a leaf or it can be a node with 2 children, which are again trees. Okay, and let's say I want to label that tree. So I have a tree and I want to, from left to right, pair each leaf with a label, which starts at 1 and then 2 and maybe, so for example, with this tree here, so precarious a balance that I start with this example tree here, and I want to write a label function that then in the end gives me, for example, pair 1, 7, here 2, 2,4, and here 3,9. So it should basically label the leaves of the tree with numbers starting at 1, 1, 2, 3, starting on the left, and leave the data that was there before alone. Just add the label. So that's the task. And if you did that in JavaScript, it would be relatively simple. So how would you probably do it? You would have some, I mean, you somehow need to know which label is next. So you would probably have like a mutable variable that starts at 1, say, and then you would like traverse the tree until you reach the leftmost child, and then you use the label from this mutable variable, and then you would increment the variable, and then you go to the next leaf and have the label, you increment your variable, and so on until you have traversed the whole tree. Now, of course, in Haskell we don't have mutable variables, or actually we do, but we don't like to use them, at least not for something like this. So you can do that in a pure way as well. And the idea is that we always keep track of the next label. So we do first a function, maybe label prime, let's say, or label, okay, which takes basically and let's say the labels, it doesn't matter, it can be ints. So the int is the next label I can use, and it takes a tree, and it returns the new next label I can use, and an updated tree where I have added labels to the tree. So we are going to implement this, but our original function, the one we want, just label, so that just goes from a tree A to a tree int, a. So we can now easily implement this in terms of this label prime. So we apply label prime with an initial label of 1 to this tree, label, and then we get this pair, but we are not interested in the new label because we are done, so we can just look at the second component. And we could be fancy and write it like this if we want to. Okay, so we need to implement this thing. So the idea is we can't mutate a variable, so we basically carry around the value of the current value of the variable all the time with us. Right, so we have this next label and the tree. And if the tree is a leaf, what do? Then we want to use this next label. So the new next label will be incremented. So it's next label plus 1. And we label that leaf. So the second component is a leaf, where the label is next label, and we don't touch the data. So that's that case. And in the node case, so we have node left, right. So what do? Well, we recursively first label the left tree. So we do label prime. I will change that in a second. So with next label and the left tree, and the result will be